Estimating the elasticity of demand. Some of you are eager to have a more mathematically based investigation of the economic theory you have studied so far. Others of you are feeling trepidation at this prospect. I hope this example will illustrate the value to you of applying more advanced mathematics in economics. Back in introductory economics, you learned that the shape of the demand curve communicates the responsiveness of the quantity demanded to changes in price. Important to know whether you are a policymaker or marketing executive. Instead of relying on the slope of the curve, we use the price elasticity of demand. The percentage change in Q resulting from a 1% change in P. Of course, since the time of Alfred Marshall at the end of the 19th century, the convention has been to draw the inverse demand curve relating P to Q. You learned to calculate an arc elasticity between any 2 points, say P1, Q1, and P2, Q2, by dividing the change in Q equals Q2 minus Q1 by the average of Q in the numerator, and dividing the change in P by the average in the denominator. That gives you the arc elasticity. The result enables us to classify demand. We speak of perfectly inelastic demand relating P to Q, perfectly elastic demand unitary elastic demand. The demand curve looks like that. And cases in between. The idea behind the point elasticity is to consider the limit as the change in P gets smaller and smaller. Intuitively, we have this expression, which we can rewrite as delta Q over Q times P over delta P, or delta Q over delta P times P over Q. Then use the calculus to obtain the final expression for the point elasticity by multiplying the derivative of Q with respect to P times P over Q. That's the point elasticity. Now, for the linear demand curves that were convenient to draw in introductory economics, Q is equal to A minus BP, so that dQ dP is equal to negative B. Given any 2 points along a demand curve, we can calculate B. And as researchers, now we're generally going to have many more observations in price and quantity. So, even holding constant all the potential demand shifters, such as income and the price of substitutes and complements, real-world data would be unlikely to fit the linear demand curve perfectly, even if that were the theoretically correct representation. When you take an introductory statistics and econometrics course, you will learn, for those of you who have taken such a course, let this jog your memory, that we can obtain a good estimate of the price elasticity of demand by estimating a regression equation in which Q is the dependent variable, P is the independent variable, and the intercept and slope coefficient of the regression equation yields estimates of A and B. Unfortunately, experience with real-world data tells us that few, if any, demand curves are really linear. Along a linear demand curve, as price rises, demand becomes more elastic. So the elasticity is equal to dq dp, which is just a constant negative b. As P rises, Q falls, and the elasticity of demand increases. In fact, the price elasticity of demand for most goods is fairly constant over the range of prices typically encountered in the marketplace, so that typical inverse demand curves are closer to the one I drew for the unitary elasticity case. Curves of this sort are rectangular hyperbolas. Stop the video at this point and see if you can show that a demand function of this sort has elasticity equal to negative b. Did you get it? Start with the definition. The elasticity of demand is equal to dq dp times p over q. So the slope coefficient dq dp is equal to negative b times a p to the negative b minus 1. To get the elasticity, we multiply dq dp by p over q, p over q, which is equal to negative b, a, p to the minus b minus 1, times p. I'm going to substitute in for q, a, p to the minus b. The a's cancel, and to see what's going on with the p's, I think it's easier if you write the exponents all in one term. So negative b, p to the negative b minus 1. P by itself is plus 1. P to the negative b in the denominator, we move it to the numerator, is plus b. So the b's cancel and the 1's cancel, and I'm just left with negative b. If reality tells us that demand follows a rectangular hyperbole, then how are we to estimate b from our data on price and quantity? The regression model econometricians have given us only provides estimates when the coefficients enter the equation linearly. We need a trick to make our dependent variable be a linear function of the coefficient. That trick is provided by using logarithms. I remember learning to work with logarithms and sines, cosines, and arctangents back in 9th grade. I'm so ancient, I learned to consult logarithmic and trigonometric tables to do calculations that any scientific calculator will do today. Mrs. Kirk told me these would be useful to me one day. I confess I've never used the trigonometric functions, although they play an important role in some advanced time series analysis, but I regularly find myself working with logarithms and the exponential function. So it will be in your interest to dig out your pre-calc textbook and remind yourself of their properties. Two of these are that the natural logarithm of the product of two numbers is equal to the sum of the logarithms of the numbers, and that the log of x raised to the power y is equal to y times the natural log of x. So, if I take the natural logarithm of my constant elasticity demand function, I get log q is equal to log a minus b log p. And that I can estimate using the regression model. Y equals alpha plus beta x. Now my slope coefficient on log p gives me an estimate of the elasticity of demand. So, recognizing the properties of rectangular hyperbolas and applying the properties of logarithms allow economists to use data on price and quantity in particular markets to drive accurate estimates of the responsiveness of demand to changes in price. Of course, it's a bit more complicated than that, but I hope this has given you a sense of the usefulness of math in terms of being able to move and actually get concrete estimates of the numbers we're working with.